I get the honor and privilege of not only talking about some of the work that I've been involved in over the last decade or so. I know I look quite young for a professor, but I do have some experience that I can kind of speak to. But also, I think I would be remiss if I did not take an opportunity to say welcome to campus. I would say maybe a warm welcome, but I guess it's a bit cooler this morning than most of our Austin mornings. So maybe that means I need to extend a warmer welcome than normal. But nonetheless, welcome to campus. We've got a lot of great ongoing things right now that I think are really relevant to actually what I'm going to talk about today as it relates to laser scanning. So without further ado, I'm going to get into talking about laser scanning. And as a way of kind of structuring my talk, I'm going to break down the acronym of my title, XYZ. I'm Canadian originally, so I'm still working on my Z to Z and you all to y'all, so bear with me. But the acronym today that I'm going to break down is basically X, meaning the existing ways that laser scanning is being used in industry. And I do know that Trimble's here, so perhaps they can spot check my talk today. But I'll talk about a few of the interesting ways that laser scanning is being used. I'll move on to the Y part of the acronym, which is perhaps how laser scanning can address or answer some of the why questions you might face in your projects. And then I'll wrap up by talking about how laser scanning can increasingly be used not just for in the field construction planning, but also for the end of life stage. So the Z or the Z corresponds to how laser scanning can be used to address the end of life of our projects or buildings or infrastructure. So to kind of help level set, pun intended, our talk today, I want to briefly give an overview of the types of laser scanners we see on the market. And I'm sure there's different ways of providing an overview of scanners. The simplest way that I can kind of give an overview is based on kind of the form function. So on one hand, and quite literally, you have handheld scanners. So this would be for very close or proximate scanning. Typically on the range of 1 to 2 meters. And the technology is such that you can produce really, really accurate data from that, sub-millimeter, depending on what kind of device you use and specify. Kind of from the top, quite literally, we have aerial scanners. So these are not actually the unmanned aerial vehicles themselves that are doing the scanning work, although photogrammetry is another common type of data collection. But these are scanners that are mounted on UAVs or drones. And with that, you have an ability to have a far larger area that you can cover, so on the order of 10 to 100 meters, sometimes even up to kilometers. Obviously, as drones can fly, you can scan. As a kind of a natural consequence to having a laser scanner mounted on a drone, typically we don't have as good of an accuracy, so on the order of 2 to 10 centimeters is common kind of category. And then finally, to help ground the conversation today, we have terrestrial laser scanners. So these are sort of middle of the road in terms of these technologies. Interestingly, you can achieve fairly similar range as aerial-based laser scanners, and it's because the devices themselves tend to be much more powerful. These are tripod-mounted units, and so you can typically scan in the same range, although you have to do a lot more traversing. But the added benefit of this is that you get an accuracy range and kind of form factor that is, I would say, really conducive to a lot more applications in construction. And so at least what I'll be talking about today focuses on this third category here, so terrestrial laser scanners, or TLS is another commonly used term. And before I jump into talking about the ways that laser scanning is being used, I want to talk about the data. So maybe just by show of hands, who's familiar with laser scanning? Okay, some. How many people here are using it on your project right now? Okay, interesting. So just to help give us an overview, the data that you get from laser scanning is basically a three-dimensional point cloud. That's where the X, Y, and Z come in from that acronym as well. And what we're looking at here is actually a simple scan that was taken of my lab, just a few blocks north of here. And if I zoom in, you can see kind of the quality and resolution of this data capture. So this was 4 scans, took me about 15 minutes to capture. And as I zoom in here, you can see what the data is. It's basically a series of 3-dimensional points that give a very accurate representation of the geometry of this wall assembly. And for that simple 15-minute process of capture plus maybe another half an hour to register this together, you'd get a data set that's quite dense, so on the order of 500 million data points. Yes, you heard that correctly, 500 million individual points that are in this point cloud. And so one of the reasons why laser scanning has become so powerful is you've got this huge, vast amount of data that you can process and utilize. Some of the ways that we can process and utilize that data, I'll kind of walk through 4. There's a lot of other applications used, I would say, within and even outside of construction, but these ones are going to be interesting for the remainder of today's discussion. So the first application is using scanning for cultural heritage preservation. And while maybe you might be wondering, okay, well, where's the relevance for construction? Because this seems to be more of an architectural preservation application. A lot of the work that goes into documenting existing artifacts and buildings can be utilized down the road for a variety of applications. One of the most notable examples was a few years back, you might recall the Notre Dame Cathedral fire. And fortunately, we had really, really good laser scans that were taken of that artifact that we could use to actually inform the reconstruction process. And so there's actually an interesting overlap here for just simply documenting the built environment and how it can directly interface with a variety of construction activities. So that's the first one. The second application that I want to highlight that laser scanning is great for is for conducting very accurate and detailed geometric analysis. If we look at a sample project just up the road here, we see that the emergence of aerial imaging, so here is like a GPS-based capture of an engineering corridor. It can be used to inform a lot of a good variety of geometry. But if we want to use the data from these, this type of capture for detailed engineering assessments, we really run into challenges both in terms of the fact that this could be from a year ago, and it really is not resolved to a level of detail that we need. And so, alternatively, we could collect a series of scans, in this case, about 40 or 50, for that same asset. So in this case, looking at a bridge. And by extracting that raw data that we get, we could crop it, convert it into a format that's conducive for a variety of different engineering analyses. For instance, maybe we wanted to do a finite element analysis of this bridge. So we see that scanning can be really powerful to inform, a lot of the nitty-gritty detail work that supports construction as well as engineering activities. The third category is scan to BIM. And this is, I would say, a very growing and stable practice for scanning. It's at least in my background, it's become one of the most mature applications of laser scanning in construction. And the reason why we see it's emerging as a really dependable practice is because a lot of the ways that we document existing buildings are simply just not to the level of detail that we need. So because of the way we document, it's still by and large a 2-dimensional drawing-based record keeping, and the fact that those records are often out of date, it really drives the need to capture accurate, up-to-date 3-dimensional information of our infrastructure. And so what scan to BIM allows us to do is for a given physical object, capture that accurately by producing a 3D point cloud, and then we could directly model on top of that. So we're no longer having to go to the field to do, physical measurement takeoff of our infrastructure, whether it be a building, a bridge, etc. So by capturing a 3D point cloud, the real dense and just the sheer quantity of data gives us a really good template to then model on top of, ultimately to enrich and to get a very well-structured building information model. So we see scanning being used to support this workflow quite a lot. And here's kind of an output of a project that I worked on about 5 years ago, just to show how accurate and detailed your resulting artifact, your BIM artifact, can be. just from a 3D point cloud. So the technology is constantly evolving. I'm sure Trimble could probably speak to that in terms of what their capabilities are, both on the hardware side and on the software side. And where the future, I think, is really going is more so on the post-processing and on the automated analysis of the point clouds, but also supporting workflows. And so this kind of leads into a natural discussion as a researcher and developer, looking at different ways that this process is being automated. And if we were to look at facility managers, whether that be a single building or here on a university campus, the process of updating facility information, so in the operations and maintenance phase of a project, even if we have capabilities like scan to BIM, a lot of work goes into trying to create that building information model. And so there's a lot of effort, even with this technological capabilities. And so if we just take a snapshot of facility operators, we see that close to $5 billion are spent annually just trying to search for, validate, or recreate facility information that are needed to support facility operations. And so in light of this, the value of scan to BIM is to kind of close the loop and to really help address this cost burden that facility operators are currently experiencing. So what I want to do is just highlight a little bit of work that my colleague, Dr. Fernanda Leite, has done through a recent project. So she is a renowned BIM expert and has done a lot of work on the scan to BIM workflow. The following slides come from a recent project that she undertook with some of her now former PhD students on a project called Living BIM. And the idea was that what if we thought of BIM not as the static, aspect of our project delivery, but what if it could live into the operations phase such that scans could help inform, and then we can simply update that building information model as changes in the built environment happen. That was really the motivation for this project. And so in the first iteration of this project, they developed this app, this interface that allowed a low-budget range camera that's mounted on an iPad, basically to traverse the built environment, to capture continuously aspects that facility operations might need to look at. And I know we're looking at just a very small kind of snapshot of a staircase here, but the application here can extend to a variety of facilities. And so what their work aimed to do is basically develop algorithms that could automatically start to understand and parse that scene. So a big part of the scan to BIM workflow involves something called semantic segmentation. Basically, how you can intelligently understand and segment and basically cluster that scene into objects. Whether that be ceilings, beams, floors, walls, doors, etc. That seems to be the biggest first hurdle when developing an automated scan to BIM process. Is just how do you tell an algorithm what objects it's basically looking at. And so the way that they approached that was through deep learning. So by training a large data set of lots of facilities information, over time you could begin to understand the physical or geometric properties of certain materials. And by training a very large data set, I think they had over 110 different environments that they basically went through and programmed. They had an overall system that was able to intelligently understand and parse out that scene. So you can see here the colors correspond to detection of unique items, whether that be floors, walls, ducts, doors, etc. And so this is just one example that we're seeing, I would say, across the research and development ecosystem for automating scan to BIM. And it's being used currently to support a lot of facilities operations. And you can imagine that, one day we can take this kind of technology and actually ingrain it right into our modeling process, such that we have got a workflow so we can keep our models up to date as changes may arise and occur. So that's the third point. One of the use cases talking about how we can use scanning to be translated into a building information model. And the fourth existing laser scanning use case that I want to talk about is actually a bit of a segue to the second part of my talk, but it's about how scanning can be used for dimensional quality assurance. So this moves us into answering some of the why questions that you might face on your project. I'm going to talk about some of the projects that I've worked on over the last 10 years or so, both in industry as well as a little bit of research work. But the three questions that I think scanning is really well suited to answer on your project are questions like, will it fit? So I've got a picture here of a square peg going into a round hole, so it might be obvious what the answer is, but sometimes you may have things that might visually not be as obvious. Second question is, maybe you're experiencing that something isn't fitting, and having a detailed understanding as to why might be valuable, and scanning can help inform this. So why doesn't it fit? And finally, to ensure that we don't have problems, ultimately another question is, how do we ensure it's going to fit next time? Or systematically, or as we continue to build and build and build, how do we make sure we've got a system in place to ensure we have things that go together properly and that fit? And I think that scanning is really well suited to answer all of these questions. And at the core of these questions is really the need to understand, to quantify, and to characterize deviations. So what do I mean by that? Well, from a design standpoint, we specify whatever it is we're building to typically have nominal or idealistic geometry, dimensions, and properties. But in reality, when we go to build, all dimensions and positions of installed materials are going to have some variability to some extent. And understanding the importance that dimensional variability plays is not a modern thing, and we can probably trace back a lot of historical projects to understand the impact and importance for trying to control geometry. So I hope you recognize this photo here. I do recognize as well that this is the reasons for this geometric situation were not because of the build accuracy, but because of the foundation settlement. But I think it really paints a nice picture of the importance for trying to control geometry. And I think actually the other interesting thing with this project, the Leaning Tower of Pisa, is it really represents our traditional approach that we face in construction when we encounter problems, which is sometimes, unfortunately, we wait till the problem happens and then we course correct, we react. And this way of reacting to problems, in some ways leads to really interesting artifacts that have probably produced billions of social media posts. But we, as an industry, can probably all agree that reacting to problems should come second place to being proactive and avoiding them in the first place. And so when it comes to quantifying and characterizing deviations, a prevailing practice has been the specification of dimensional tolerances. So we may not know, what the true impact of variability is, but if we can keep that confined to acceptable limits, then at least we mitigate some of the problems that we might face. But I want to posit that even if we specify tolerances, how do we know we comply with them? And in my experience, I've worked on many job sites where the tolerance specification was just something that was written on paper, and there was a complete gap between what that intention was and what was encountered in the field. And I think that this is really where laser scanning can help kind of address what this gap is between the idealistic, if it's a 2-foot span of something, we put a plus or minus value on that, to understanding what the actual impact of that variability has. I think scanning can help address that. And if we look at current technologies, there's a lot of great capabilities that manual and analog equipment plays. So even in my experience, whether I was using scanning, I would try to communicate my findings through manual equipment such as tape measures and plumb bobs. And so while I don't see those, at least in the immediate time frame, going away, I think the value that scanning brings is kind of going from this analog environment to a digital environment. And while that may bring some level of objectivity to how we measure and quantify things, another benefit is moving from single point measurements to kind of a mass environment of just a sheer quantity of data that can help inform and do things that those analog or manual devices will never be able to do, just because they're set up as to be single measurement devices. And so this is really one of the added benefits of scanning, and one of the ways that it can really empower the process of quantifying geometry in construction. And so there's two workflows I want to highlight really quickly of how scanning can help characterize deviations. And the first is simply, you can just take a series of scans and compare those data sets directly. The kinds of comparisons that you can draw, and what you do is basically simulating virtually ahead of time if you're going to have any geometric problems. And the second workflow, as shown here on the bottom, is if you have the ability to leverage an existing 3D model. And by taking a scan of whatever it is you're building And overlaying that on top of that 3D model, you can actually map and visually see the build deviations. And so both of these workflows, scan versus scan and scan versus BIM, have become kind of a staple in industry in terms of quantifying and characterizing deviations. And to kind of show some of the work that I've been involved in, here's a simple project where I was working in off-site construction, where the question was, how do we ensure not necessarily that our build quality, what was being done in the factory was built to a suitable accuracy, but when we brought those units to the job site, how do we know that those interfaces at the job site are going to correspond to where they need to be? And so that's where taking and comparing scans of these two environments ahead of time, you can perform virtual fit up and make any corrections before you show up at the job site, where then the cost and the schedule implications are obviously a lot more impactful if you're going to have problems. And then the second workflow that I've been involved in is where you can leverage that idealistic geometry. You can take a scan and compare that to understand ahead of time if you're going to have any problems. And so here is just a simple figure of showing where a door is fitting into a rough opening. And so while it might be simple in nature, I think the capabilities that scanning allows us to do is to move beyond just simulating if something is going to fit, to having a more systemic understanding of when we do encounter problems, why is it happening? And so in another project that I worked on, there was a contractor who was trying to install these floor cassettes into a floor frame and was finding time and time again that there was some sort of misfit. And after exhausting what we can measure with a tape measure, we were not figuring out what was going on. And so introducing scanning into the equation allowed us to understand that it was actually the welding process. So in this case, the frame, how it was being welded, was causing weld distortions that were really hard to pick up from manual measurement devices. And so it just shows that by bringing scanning into the workflow, we could actually systemically understand and quantify the issues of this fit up. And so I think that's one of the added benefits, is that the sheer quantity of data that you can get to inform kind of the problems that we encounter is an ability to shift away from just understanding if something is going to go wrong to moving into a phase of truly understanding why something's not working, to really the third step, or the third question we face, and there we go, is how do we ensure that we can guarantee that it's going to fit? And I think this moves into another territory now. I think that this involves not just understanding kind of one process that impacts geometry. And if you can advance just to the next slide for me here, or the animation. There we go. It's a matter of understanding holistically across your project. There's going to be a wide range of factors that could potentially impact geometry. And by trying to characterize the relationship of those factors on the overall accuracy, it gives us an ability to move into understanding which of these factors are going to be most impactful for accuracy. And I'm just running into issues with the advance of this here. So I had 3 questions basically that show up next, which is understanding what factors impact accuracy the most, how to put proper controls in place, and then where scanning can really be used is to try to monitor the performance of those controls. And there we go. We got action here. I think the computer needs a coffee break, perhaps. Okay, I might need some help if someone can advance the slides for me here. Because my, there we go, okay. Okay, so the value of this is that by understanding holistically your project and those factors that might impact where you could have problems, by introducing scanning sequentially and by trying to bring in controls, you can go from a project like this, which had all sorts of fit-up problems, to a project like this. The exact same product was being built, but by bringing in controls, in this case, ensuring, just by example here, controlling the flatness of the floor before doing welding, then you guarantee that that geometry is being locked in, is flat, and then that has a ripple effect. Anyways, the moral of this is that you can move from a project with all sorts of geometric fit-up problems to a project where you significantly minimize those. And scanning can really help empower that process. A final question before I move into the last part of my talk is a question I haven't written down, but I think has become more and more relevant as not just the implementation of scanning has become more prevalent, but also the supporting algorithms that interpret it have really evolved, which is, will it pass inspection? I think this is something where I've seen recently there's been a lot of attention and development on. So we're looking here at two side-by-side comparisons. This is a mock-up of a wall assembly in my lab. And for those who are more into construction than I am, please go easy on me. I understand that this is probably filled with all sorts of code violations, but maybe that's perhaps the point of my illustration. So as sort of a layman looking at this, I could say side-by-side they look pretty good. But if we were to bring in scanning, we would find that by comparing these, there's all sorts of quality problems. Things like missing components and things that are out of tolerance. And so what scanning provides is this objective way that you can assess and perform inspections on your job sites. And I think that that's become kind of a way of guaranteeing kind of an added layer of protection, so to speak, so that, you know, humans are fallible and we're bound to miss things from time and time again. And so scanning provides us that additional kind of blanket or cushion to make sure that we're building the way we should. And so the last part of my talk, I want to kind of shift gears a little bit. I've been talking a lot about kind of examples and details of how we can use scanning to inform, you know, the actual construction process. But I want to also highlight a little bit of how scanning can be used at the end of life of our projects or our infrastructure. And to kind of help set this conversation, I want to think and talk broadly here about the environmental impacts that the built environment has. I know it's a kind of a play on words, the built environment and the impact on the environment. But if we look globally right now, a third of all CO2 is contributed to the built environment. A third of all embodied energy is contributed to the built environment. And over 40% of all of our landfills are attributed to the built environment. And so if we want to understand how we can really shift our industry forward to reducing this environmental burden, I think one of the ways and kind of next steps that we need to take is to look at how we're managing resources at the end of life stage. And so I'm currently working on a project actually based right here on UT Austin's campus, where we are studying an active demolition project. You might have actually seen it on the drive-in. That's a big kind of dome-shaped building. And if you have time at the end of this event, I highly encourage you to take a drive-by because it's really, really fascinating just to see all of the prep that's going into that demolition project. But fundamentally, what we're trying to understand on this research project is, you know, theoretically, as materials reach their, so to speak, end of life, there is a theoretical way of mapping how much residual utility is still in those materials. And it's unfortunate that by and large, we end up towards the bottom of this pyramid where, you know, we resort to landfilling and maybe some recycling, but there's a lot of embodied energy and embodied carbon that we're simply just wasting by not leveraging opportunities that are afforded by things like better reuse and better upcycling if possible. And so what we're working on in this project is to say, are there certain classes of materials that lend themselves a stronger ability to being reused than others? And by looking at existing classification systems that we would be all intimate and understand, things like master format and uniformat, is there a way that we could augment these classification systems to understand which materials could, in theory, be more readily reused than others? And so here's the project that we're working on. Again, if you have a chance at the end of this conference, highly encourage you to drive by. Looks a lot different now, but there's two buildings on this premise that were the ones actually fully gone now. The smaller, maybe I can point it out here with my laser pointer. So this building here is fully demolished, and this one's currently in the process of having the enclosure being selectively demolished. It's what used to be our former basketball stadium. And what we're doing in this project is trying to do a quantity takeoff, just to start scratching the surface of understanding, you know, what types of materials can be reused. And so we're looking at things like interior doors, carpet tiles, and ceiling tiles, which have a higher theoretical residual value. We're also looking at structural materials such as the precast panels on the outside. And in going through this process of doing the quantity takeoff, we saw the value that laser scanning can provide. So we realized early on that the building was not really documented in a way that was conducive to performing this assessment of reuse. And so we did a series of comprehensive scans, both outside the big stadium and inside that smaller building, to understand, could we use this data to do a better and more accurate quantity takeoff? So for the panels that I just showed, understanding the exact dimensions, which happen to be missing in the original drawings, as well as understanding that typically we've got a very limited time that we can go onto a job site before things like asbestos abatement happens. And so we really understood the value of leveraging laser scanning to create this digital artifact that then we could use and plan on top of that, rather than requiring being in the field to do that assessment. And while this helped inform things like performing a better and more accurate quantity takeoff, where we see the future of this is a future where this is fully automated. So we could bring laser scanning to the job site, digitizing that job site, and automatically understanding and interpreting that scene in light of materials that are more readily reusable than others. And so this might still be kind of far out there, but I think that there's a big opportunity that laser scanning can bring to support how we can be more sustainable with resource management at the end of life stage. And so with that, I hope you found some of this interesting. I'm happy to answer any questions you have. It's an area that I'm really passionate about. And so with that, I want to thank you for your time and attention, and I hope I was not too long here. So thank you.
Perfect. Thank you very much, Chris. Because we're not too bad on time, but running slightly over. I'll open it up to start off with to the audience. If anyone has any questions for Chris, please put your hand up and Steve will hobble over to you.
Bronco. Hi, that's really interesting talk. My name's Adrian Pritchard. I'm with a very small boutique corporate finance firm called Nash and Co, which does mergers and acquisitions in the construction sector. So I'm also a non-exec director of a facilities management business in the UK, and I was very interested to hear your the piece about how laser scanning can assist with facilities management. One of the problems that we come across is identifying assets and having an asset register that is up to date and accurate, but also one which can predict and talk to maintenance schedules and perhaps even predictive maintenance. Just wondering, when you were doing the scans, I could see infrastructure like piping and some walls and bits and pieces like that, but you didn't go into the machines, for example, an air conditioning machine or a heat, a boiler or something like that. And I'm just wondering, is there a kind of an interface between the laser scanning and the asset register and bringing value to our clients in terms of saying, look, this is the facility you have, these are the machines you have, in a much greater degree of accuracy?
Yeah, that's a great question. While I don't have personal experience with that, when I was doing my PhD, my advisor at the time was working on this project where it was really about trying to go into a facility where there was manufactured equipment, and if you had the ability to augment, whether it's the scan or even simply just by photos, basically doing equipment tagging. And then you could create in the background kind of this registry. So I think that the technology's there. I think that the challenge is in understanding, at least in part, how do you structure the resolution of that capture that's required, as well as understanding what tool is really good for the job. And that's where I think, at least in the scanners that our research lab is using, it's a laser unit augmented with a camera. And so there's a way of kind of leveraging both of those data sets that I think, depending on the workflow, you could really leverage things like even machine learning on top of just the images. And if there's things that are condition-based that you want more, insight from a geometric standpoint, then maybe that's where you tap into the 3D point cloud aspect of it. But I am aware, at least in principle, of the attention towards trying to classify and tag equipment and facilities. And of course, it has significant interest in industry.
Hey, my name is Kemi. I work in materials testing and inspection space. I noticed that you mentioned something when you were showing your lab, just on like making or using laser technology to increase the quality of the inspection, like whatever that looks like. I was curious about what like you see, you know, how you see the future of inspections and, you know, laser technology and how that all integrates, including BIM and all that stuff, and if there's any use cases right now of that happening.
Yeah, so before starting in my current role here at UT Austin, I was working for a construction company where that laser scan was vital for our internal inspection processes. We needed to build accuracy that, you know, we were using that technology to inform and give us confidence that when things showed up on site, things were going to stack together properly. So from a strict geometric and accuracy standpoint, the need and the application are already there. Where I think the value at an industry standpoint is, regardless of that accuracy, I think that one of the big constraints is just how much schedule interruption your inspection process can take. And what I'd love to see is whether you can have the building inspector gain confidence in this objective data capture. And if you could have, because I can envision it, you could digitize it continuously as you're building and have all the algorithms and methods in place that tell you if you have or are building properly. But I think really the next step is getting those building inspectors to have confidence so that they can do things. And we actually saw some interesting examples during COVID where the building inspection process was actually done virtually, remotely. And so I see a whole range of things that can be facilitated through digital technology, scanning being part of that bigger picture.